All right, yeah, we're going to start with 8, where we have the gravitational force between two volleyball players. With these masses, what is their separation? All right. So that, of course, it's a gravity problem, so it's going to be a written y. You got it? Good. So this is number 8. And maybe make that smaller. 36, I think, is going to be too big. 4. I always start with the y and then I move on to the how. Because see, I want to model what should be in the y and what should be in the how. I will be. As long as we don't spend the next 40 minutes on the y and then we run out of time. And that'd be a really long time to spend on a y.
That would be crazy.
That would be. Should we talk about that? Let's see. The players are attracted to each other since they both have mass. The closer they are together, the stronger the force by an inverse square law. More massive, remember, not the more they weigh, the more massive they are, the stronger the force. I think that's it. That does it. Yes, sir.
So why is like you don't have to get that long? It is big line to these two. Yeah. Like this can be a long.
Yeah. Yeah. I just kind of, back when you used to fill these out by hand, I threw lines there. I just haven't redone my background.
So you just basically stand.
Well, let's see how I done my rubric, right? Clear understanding of the physics of the problem. So if I was reading this, I'd say, okay, they understand, players attract to each other. I might want to add in here by a gravitational force, since they both have mass. So I know it's their masses that's creating that force, and it's a gravitational force. So that is the physics. Then, do I see, okay, if they're closer, it's going to get stronger, and it's inverse square, and they're massive, the stronger. So everything is based on their mass and how far apart they are. And that gives me that clear links to problem, because I'm talking about them and the players, and not just everything is connected to everything else with mass. That doesn't address this problem. And then in no way did I say, hey, I'm gonna solve it this way. I've got in there that the universe works this way because gravity is created by mass. That's clear, but I think, if I was reading it. But I didn't say I'm going to use universal gravitational equation and put in all these numbers. You wouldn't do that in the Y.
You wouldn't even put it there, but.
Nope, no equation ever in the Y. If you ever find yourself writing an equation, take it out of there. Get rid of it. Yeah. Some people like to put values in there. I don't, but you could. I would take off from that. But any equation, or I'm going to do this, wrong. You lose that 20% right away.
Wow. That's
There were a lot of killers on the test that way. You may be able to see you know, just, all right. So now I'm on to the how.
Where's our test?
Yeah, I've created monsters. So I need to start with a valid physics equation. And it's about gravitational force, so I'm going to grab the gravitational force one. Right here.
Really concentrate. Was it in October?
Yeah.
It was like the last thing in last year. Sorry, I need this. There we go. Alright, so there's the equation. And are there any constants in there that I need? Yes, big G, the universal gravitational constant. And nicely, that's right here on my equation sheet on the second page of it. So I don't even have to memorize it. Right here. Yeah. Second page of the equation sheet. Alright, now I'm going to need to look at the problem. Might not get comments until I return it, sorry.
Oh, see?
I got your hopes up.
Yeah, thanks for that.
And I dashed them.
Well, if it was going to be a freak out, might as well push the freak out of the way.
Alright, so let's see, I am told the gravitational force. I'm told the mass of each one. Does it matter which one's M1 and which one's M2? No. And then I want to know it. So they give me kilograms, they give me newtons, and they want the answer in meters. But is that going to, let's see, is that going to work out? Well, yes, because big G is in newtons and meters and kilograms. So yeah, I don't even have to do any unit conversions. So 3.5 times 10 to the minus 7 newtons. So that's my F sub G. 3.5 times 10 to the minus 7 newtons. I'll tell you that those type numbers are going to cause some people to screw up because they don't know how to use their calculator. Right? They don't know how to use the exponent key. If you don't know how to use the exponent key, or I call it the EE key on your calculator, find someone who does, find me. Learn how to use it, because you can cause all sorts of problems with if you don't know how to use that. And then big G. Use my connected letters. Still getting this board down. Over, and then I don't remember my two masses off the top of my head. 61 and 79. And R squared. Yay! One variable left, one equation. Does anyone need help with the algebra of how to do that? All right, so Megan, I think, asked me to do the algebra here. So I'm glad to do that. So the way I do the algebra is I go to that incredibly helpful site called Physics is Fun, and I scroll down to my math solvers because I don't want to do algebra. Why should I do algebra? This isn't algebra class. And these are available on all assignments and evaluations. Oh, that's why it said on the top of the test, you can use the solvers. That's probably what happened to
Wait,
Lisa.
really?
So I'm going to go to Wolfram Alpha, and I'm going to put in my equation. So I'm going to put in 3.5, and here I use E, because, just the letter, because that's what they want. Actually, I use capital E, I believe. Let's see, -7. Come on, where's that? -7 equals, parentheses, 6.67 E -11 times 6179 times 61 times 79, close parentheses, divided by R caret 2 r squared equals. And it tells me r is 0.958313.
I can see it.
Oh.
Sorry.
Wait, is that always the force of gravity on
Is what always the force of gravity on Earth?
Earth?
That's the universal gravitational constant. That's the same everywhere in the known and unknown universe.
I gotta memorize that.
Can you
Actually, I stored it in my calculator. Yeah.
can you go back to the like what you typed into the calculator, please?
Right, cool.
Yeah, thank you.
Yep.
So we can use this calculation on that.
Of course. I want to know if I got it right. I should probably write my final answer and correct sig figs and everything. 0.958 meters. That 9 is horrible. I gotta get better. I gotta practice. All right, on to 12. Asking me what altitude above the Earth's surface is the gravitational field strength equal to G over 5. All right, so now we gotta do our Y for this one. Start off simply. The Earth has a gravitational field since it has mass. The further you are from the center of the Earth, the weaker the field. At the surface of the Earth, this field has a strength of little t. I might even put the field is based only on the Earth, not the object.
Yeah, but I thought, that was the radiation there.
Alright, because I want to show that I understand that field is different than force. Alright, because since the force would be based on the Earth and the object, this is just based on the object. I think I'm going to add another line in here. How far you are from the center of the Earth is how far you are from the surface of the Earth and the radius of the Earth. Because what's it called that describes how far you are from the surface of the Earth? What's the word for that? Like you get in a plane.
Altitude.
Altitude. So how far we are from the surface of the Earth, from the center of the Earth, is whatever altitude we're at plus the radius of the Earth. All right? Yeah. All right, let's do the half. Let's grab my equation. My sipping tube. I don't feel like writing it. We got that. This is our gravitational field strength equation. Right? And we need our universal gravitational constant again. We also need the mass of the planet, or the thing that's creating the gravitational field. What planet is creating this gravitational field that we're interested in?
Earth.
Earth. So we're going to need, oops, I want this. So let me grab big G first. Big G into this, there we go. And then I need the mass of the Earth because it's creating, and I also need some, I think I'm going to need the radius of the Earth. Remember, this RP is how far you are from the center of the planet. Remember, doesn't stand strictly for radius, but how far apart the two things are. Okay? But I think I'm going to need those factors about the Earth, so they're right here on my equation sheet also. Let's grab those. Oh, this is getting pretty big. Alright. So I think I have all my factors now. So, let's see. So I'm looking for the gravitational field strength. I have big G, so I'll use that. It's the mass of Earth, because that's the planet I'm around. And I'm told I want to know, let's see, at what altitude above the Earth's surface is the gravitational field strength. So, I not only want how far, remember this R is how far I am from the center, which is the radius of the Earth plus my altitude. Yes? So if I was to draw it, here's the Earth, here I am, this is the radius of the Earth, this is my altitude, we use the variable ALT. Good with that? So that's what R is. So here I have radius of the Earth plus ALT quantity squared. Now it's substitution time. I know what G is. Oh, wait a minute. I probably should have grabbed from my equation sheet, grabbed little g, which is 9.81 newtons per kilogram. So this is little g over 5 for me, I think. Yeah, everyone had different numbers it was over, right? Yeah.
Oh, yeah.
Yeah. So now really it's substituting in. 9.81 newtons per kilogram over 5 equals 6.67 times 10 to the negative 11 newtons per kilogram squared. Mass of the Earth, 5.98 times 10 to the 24th kilograms. All over radius of the Earth. Now, I nicely looked and everything was in meters and kilograms for me. And the only variable I've left in that is altitude, or alt. And so I'm going to solve for alt. This is where, like Wolfram is your friend. Let it do the work. And if I look, I'll end up with that in meters. Sunday.